everybody. The AP Calculus A, B, and BC exam is right around the corner, and I wanted to give y'all a quick MCQ type review for both AB and BC condensed into one video. So the procedure will go that I give you a problem, you can pause and solve it yourself, and then you can view my steps to solving the problem and the correct answer. Okay, so I'll give you a few seconds to tackle this problem right here. Okay, hopefully you've solved it. So for this limit here, we have the limit as x approaches 0 of this stuff, and if you just plug in x equals 0 into all this stuff, you're going to get a 0 over 0, and that's going to be your indeterminate form. So, of course, you're going to want to use L'Hopital's rule, which is taking the derivative of the top and the bottom, and that's going to be equal to what we have here. So if we use L'Hopital's rule to avoid this indeterminate form, we have the derivative of the top, derivative of 9x is 9, the derivative of sine x is cosine x, and then we have the derivative of x squared, which is 2x, plus the derivative of sine x, which is equal to cosine x. And now, it's not equal, sorry. Now, our limit, if we just plug in 0, we should get 9 minus cosine of 0 is 1 over 2 times 0, which is 0, plus cosine of 0, which is 1. So this is going to be 8 over 1, which is equal to 8. So 8 is the answer for this limit. Okay, our next problem is going to be a limit in its, or a derivative in its limit form. So in this case, we'll have limit as h approaches 0 of the natural log of 4 plus h plus ln 4 over h. That'll actually be a minus. Okay, so let's find this limit here. So I'll give you a few seconds. You can pause the video if you want. Okay, so as you can recognize here, this is sort of the derivative definition here with the h approaches 0, and we have that same structure. So what this is saying is this is talking about the function, the natural log function, and this is taking the derivative of it at 4. So the derivative of the natural log function is 1 over x. So f prime of x is equal to 1 over x. And then if we plug in f prime of 4, you're just going to get 1/4. So the question may seem tricky at first, but you just have to realize what you are dealing with in this case. So the answer is 1/4. Now let's do some derivatives. So we're going to say that we have a function. Okay, for our next question, let's say y is equal to 5x times the square root of x squared plus 1. Let's find y prime of 3. I'll give you a few moments to solve this problem. Okay, So for this problem, this is going to use a combination of product rule and chain rule. So here we have our two terms. We have a 5x and we have a root x squared plus 1 here. And we're to take the derivative, what we're going to do is we're going to have to use the product rule. And remember that the product rule is the derivative of the first, which is 5. You keep the second. And then what you do is you add 5x. And then what you do is you take the derivative of the second one now. So the derivative of the square root of x squared plus 1 is going to be equal to 1 over 2 square root of x squared plus 1. So if you would just ignore this in the inside, you'll get this. However, since the chain rule does apply, you need to make sure to take the derivative of the inside. So that'll be 2x. So you're left with x over x root x squared plus 1. So let's write that down. 5x squared, and then we'll put it over root x squared plus 1. And so our final answer is going to be, when we plug in 3, is going to be 5 root 10 plus 45 over root 10. And you do not need to simplify any further for this problem. So if you had an answer similar to this or a more simplified version, that is the correct answer. Let's move on to the next problem. Okay, we're going to have the limit as h approaches 0 of arc sine of a, some value a, plus h minus arc sine of a over h is going to be equal to 2. So let's find the value of a that satisfies this limit. I'll give you a few seconds to solve this one. Okay, so for this limit, what we're talking about, this is the structure of the derivative of arc sine. The derivative of arc sine is 1 over the square root of 1 minus x squared. And in this case, we have a squared as our value we plugged in. So a is just some random value. So we're going to set 1 over the square root of 1 minus a squared equal to 2. So if you do the math on this, you're simply going to get that if you swap these two, you're going to get 1/2 is equal to square root of 1 minus a squared. If you square both sides, you're going to get 1/4 is equal to 1 minus a squared. You're going to get a squared equals 3/4, and that a in total is equal to the square root of 3 over 2, plus or minus square root of 3 over 2. And that is that problem. Pretty simple once you get the pattern. Okay, let's move on to the next problem. Okay. So, okay. Let's say that the limit as x approaches infinity of the function f is equal to 0. Let's say we're given 3 different limits here, or 3 different functions. Which ones of these satisfy this condition? So, first one is ln x over x to the 99th. The next one is e to the x over ln x. And then the next one is x to the 99th over e to the x. So which of these satisfies this equation? It could be more than one, it could be all, or it could be none. So for this problem, we're taking the limit as x approaches infinity. Let's go to option 1 first. We have the natural log of x and x to the 99th. So if we use the L'Hopital's rule, because we're getting an indeterminate form if you plug in infinity on the top and bottom, if we use L'Hopital's rule, we're going to get that this is equal to 1 over x divided by x, the derivative of x to the 99, 99x to the 98. And as you can see here, that x moves down and creates this. So this is what happens when we take the derivative and use L'Hopital's rule on this first one. And as you can see here, since the degree is so much bigger on the bottom, as it approaches infinity, it's going to approach 0. So in this case, option 1 is a correct answer. Okay, so for option 2 here, we have e to the x over ln x. So if we plug in infinity, we're just going to get an indeterminate form. So what we want to do is we want to use L'Hopital's rule. So e to the x over 1 over x. And because we're dividing by a fraction, we're really multiplying by the reciprocal. So x e to the x. And no matter how many times you do this, you're still going to get the same result of something being multiplied by something, and you're going to get an infinity times infinity indeterminate form. So in this case, this is not one of the options. Now let's check number 3. So for number 3, if we take the derivative, we get x, or we get 99 x to the 98th over e to the x here. And if you see this right here, this doesn't really give us much information, because if we plug in infinity and infinity, we still get that infinity over infinity thing. But what we have to notice here is that imagine if we took all these derivatives to get rid of this x, and because e to the x is always its derivative, it would always stay the same. So if you kept piling on derivatives, if you took 99 derivatives of this, you'd get 99 factorial over e to the x, and that would just be simply by moving those exponents down over and over again. And your limits would in turn approach 0. So that one's a little bit tricky, but that one is also approaches 0 as x approaches infinity. Now let's move on to another problem. Okay, so let's say we have an infinite series. Let's use white here. infinite series n equals 1, and it's going to be given by a sub n. And we're going to be given that the first term in the sequence is equal to 16, and that the following is true. an plus 1 over a to the n, or a sub n, is equal to 1/2. Okay? And that is obviously for n greater than 1. So we want to find the sum of this infinite series. So I'll give you a quick moment to find this one out. Okay, so for this one, the strategy is primarily conceptual. So for this problem here, what you want to focus on first is not any of this information, any of the first information, but focused on what it means by this information here. So this information, if we cross multiply, we're going to get a to the n, or a sub n, is equal to 2a n plus 1. So what this is saying is that each time that you have to go to the next term, you're multiplying by 1/2. So in this case, we can essentially call this is a geometric series, So we can write this as our infinite sum of our starting value, which is 16, our common ratio, we're multiplying by 1/2 each time, and then we'll have n minus 1. And so for our infinite geometric series, what's going to happen is that we're going to remember to use our formula that if r is in between 0 and 1, or the absolute value of it, we used this to determine what it's going to converge to. So in this case, we have 1 over 1 minus 1/2. So this is equal to 2. Because 1 minus 1/2, this is 1/2, and 1 over 1/2 is simply equal to 2. So we know that this part sums up to 2. So 16 times 2, this is equal to 32. And that is the answer for this sum of a geometric series. Let's move on to the next problem. Okay. So we have the integral from 0 to 4 of x over the square root of x squared plus 9 dx. So find this integral. Your answer should be numeric. I'll give you a few moments to solve this problem. Okay, so as we can see here, we have an x squared on the bottom and we have an x on top. So those terms are only 1 degree apart. So it looks like we do not need to use trig substitution or anything like that. We only need to use u substitution. So for this problem, we're going to let u be equal to x squared plus 9. That doesn't really look like a 9. There we go. And then du is going to equal 2x dx. And so if we want to replace dx, we're going to want du over 2x is equal to dx. So now let's take everything into the u world. So we have the integral, and let's update our bounds because now we're talking about a different system. So if we plug in 0 and 4, if we plug in 0, we get 9. If we plug in 4, we get 25. So now it's the integral from 9 to 25 of x over, and then this is the square root of u, and then this is times 2x, and then we have to remember we have our du over 2x. So here, let me separate them to illustrate exactly what I'm talking about. So we simply replaced x squared plus 9 with u, and then we also have this divided by 2x form, which is going to completely cancel out the x's. So now you're just going to be left with 1/2 integral from 9 to 25 of 1 over root u du. So just use the power rule for integration. So of course add 1, so this is u to the 1/2, and then this is divided by 1/2, so this is going to be equal to 2 root u. So let's erase this real quick for space. This is going to be equal to 1/2 times 2 square root of u, and this is from 9 to 25. So, using the fundamental theorem of calculus, this is 1/2 times 2 root 25 minus 2 root 9. So 2 root 25 is 10, and 2 root 9 is 6. So 10 minus 6 is 4. 1/2 of 4 is equal to 2. So the answer for this problem is 2. Let's move on to the next one. So for this next one, we're going to have a parameterized curve. So we're going to have x of t is going to be equal to t squared over 2. And y of t is going to be equal to t cubed over 3. So we want to derive or find the integral and solve the integral that gives us the arc length from p equals, and then we're going to have t equals 0 to 1. And so we're talking about our arc length. So we have to remember the formula for this, and we have to take everything into account. So find the integral expression and then give the numeric answer. Okay, so if we remember, our formula is the integral of the square root of our dx dy squared plus your dy dx squared, and then for this right here, or not d, sorry, dt with the parameter t, and hold on, you just switch these parameters. Okay, so this is the formula for the arc length. So arc length is equal to this. And so if we plug in x of t, the derivative of x, which is our function with respect to t, if we move the 2 down, it cancels out with the other 2. So this is just equal to t, and t squared is equal to, t squared is t squared. For dy dt, what we have is if we move the 3 down, it cancels with the divided by 3. So now we're just left with t squared, and t squared squared is t to the 4th. And so this here, along with our bounds from 0 to 1, that is our integral expression for the arc length. Now, let's find the arc length. So I'd say the best way to do this is to use U substitution, I'd say. So let's first factor out a t squared times t times 1 plus t squared, 1 plus t squared, and then we're taking the square root of this, integral 0 to 1 with respect to t, and so this root, now the root and the square cancel, so we're just left with t, and then now we have t times the square root of 1 plus t squared dt. So now what we can do is we can now apply our rules. So let's let u equal 1 plus t squared, du is equal to 2t dt, and so du over 2t is equal to dt. So that means that when we rewrite our integral, we're going to have t times the square root of u over 2t, and then this is going to be all changed to du, is going to be our new integral. And then if we change it, if we do a u substitution, we also need to change the bounds. So let's just plug in 0 and 1 into u, and then it'll change our bounds successfully. So if we plug in 0, we'll get 1. If we plug in 1, we'll get 2. So here, the t and the t cancel, and we can just move the 1/2 to the outside, which is what I prefer to do. 1/2 from 1 to 2 of root u du. So in this case, this is going to be 1/2 times, remember that the derivative of the square root of x, or sorry, the integral of x, the square root of x, is x to the 1/2. So this is just going to be 2/3 x to the 3/2. Okay, and then this is going to be from 1 to 2. Let me extend the page here. I know this problem is very long. So we're going to have 1/2 times 2/3 times 2 to the 3/2 minus 2/3 times 1 to the 3/2. And you can see here that it's going to get a little complicated, and the answer isn't going to be an exact number. So for this one, 1 to the 3/2 is just 1. So this is going to be minus 2/3. For this one, this is simply just going to be, this one here is going to be 2 root 2. So this is going to be 4 root 2 over 3. And this is going to be all multiplied by 1/2. And so if you combine these, minus 2, 4 root 2 minus 2 over 3, this is times 1/2. This is equal to, we just multiply the bottom by 2, and we get 6. So this will be the final answer, and you can plug this into a calculator for an exact answer. Anyways, let's move on to the next problem. Okay, for this next problem, we have the integral from 0 to 1 of 5x plus 8 divided by x squared plus 3x plus 2. So, solve this integral. You should receive a numerical answer. Okay, so for this problem, it is very important to recognize that we need to use partial fraction decomposition for this problem because we have a polynomial on top and a polynomial on the bottom. So it's probably best, since for partial fractional decomposition, it's probably best to factor out the bottom. So let's say that this is equal to, we're going to keep our integral, we're going to keep our 5x plus 8. If we factor out the bottom, we get x plus 2 times x plus 1. X plus 2 times x plus 1. And let's use the cover-up method of partial fraction decomposition to decompose this specific example. So what you're going to do is we're going to first look at this one right here. So let's have x minus 2. What we're going to do is we're going to cover it up, and then we're going to plug in whatever would make it 0. So whatever makes x plus 2 equal to 0, which is negative 2. And if we plug in negative 2 into here and into here, you'll get negative 10 plus 8, which is equal to 2, or negative 2. And then over negative 2 plus 1 is negative 1, which is equal to 2. So that's how we know that our first one is going to be 2 divided by x minus 2. Okay. I think this is right. Yes. So for the next one, we're simply going to just do the opposite. So let me rewrite x plus 2. Now we're going to cross out this one, and we're going to put in negative 1 here and negative 1 in here. So in this case, we're going to get 3 over 1, which equals 3. So this is going to be, that's going to be our b value, which is the one on top here. So 3 over, and then x plus 1. For this partial fraction decomposition here, we can now just use our natural log rules in this case for this one. So we're going to have in total 2 ln of x plus 2 plus 3 ln of x plus 1. And then this is all going to be evaluated from 0 to 1. And so when we do evaluate this, we could just plug in the values, but what I want to do is I want to be a little more efficient and just combine these expressions. So if we move the 2 up here and the 3 up here using our log rules, and then combine the 2, we're going to get ln of x plus 2 squared times x plus 1 cubed. And then this is going to be from 0 to 1. Now we can just combine it all in 1. So if we plug in 1 here, what we're going to get is we're going to get ln of 9, which is 3 squared, times 1 plus 1, which is equal to 2, and 2 cubed is 8. And we're going to subtract. If you plug in 0, we're going to get the natural log, we're going to get the natural log of 4, which is 2 squared. And this is times 0 plus 1, which is 1, and 1 cubed is 1. So the natural log of 72 over the natural log of 4, or minus the log of 4, is just going to be the same thing as ln of 72 over 4, which is equal to natural log of 18. And you can plug this into your calculator. And here you go. That is the answer for this one. Let's move on to the next problem. Okay, so here we have an infinite series n equals 1 of n minus 1 x to the n over n squared times 6 to the n. So we want to find the infinite sum at x equals 6. So we want to find, does it converge, does it diverge, and if it does converge, where does it converge? So I'll give you a few seconds to solve this problem. Pause the video if needed. Okay, so for this problem, we're simply just going to follow the instructions they gave us by plugging in 6. So in this case, we're going to have our infinite series n equals 1 of n minus 1, and then we're going to have, instead of x is 6n, 6 raised to the n squared times 6 to the n. So as you can see here, our 6 to the n's cancel, and we're just left with a series n equals 1 of n minus 1 over n squared. And so what you're going to want to do now is that now that this series looks a little more familiar, you're going to want to use a comparison with another one of the famous series to see if it converges or diverges. So in this case, we can compare this with the infinite series for 1 over n. Because the degree on the bottom is 1 more than the degree on the top. So that's our comparison. And since this one right here, this one diverges, that means that this one diverges as well. So the final conclusion is that at x equals 6, it diverges. Let's move on to the last problem. Okay, so we have at last the integral of e to the x cosine x dx, and this is just a definite integral. So solve this integral, and then I will show you how to do it. Okay, so for this integral here, we're going to want to use what's called integration by parts, where we have two things being multiplied by each other, and this is kind of like the product rule, but for integrals. So what I like to do is I like to make what's called a DI table here with derivatives and integrals, and then on the side, we're going to alternate plus, minus signs. And just write a few of them. You won't always need all of them. But we want to choose one of these terms, either e to the x or cosine x, that we want to take the derivative of or the integral of, and whichever one's easier. In this case, they're both pretty simple, but what I like to do is just to make sure I don't make mistakes, I'm a little more familiar with the derivatives of the trig functions compared to the integrals. and then if I integrate e to the x, it's always going to be e to the x. So I'll just choose that one for simplicity, because derivatives are usually simpler than integrals. So let's just go down the chart taking the integrals and derivatives. Of course, for this side, it's simply going to be e to the x. For here, we'll cross multiply, and then what we're going to do is then we're going to have this integral right here that we'll evaluate. So this is e to the x cosine x, and then we have a negative sine x, so that's a positive e to the x sine x. And so this, and then what we're going to do is negative cosine x times e to the x, which is negative e to the x cosine x, so negative integral of e to the x cosine x. And it seems like we've just came in a full circle. However, if we realize that this is in fact equal to our integral, we see that we can actually move our integral to the other side and say that, let me just erase this, that this is equal to 2 integrals of e to the x cosine x dx. So since we want to find just one of the integrals, we can just divide by 2. So divide by 2. And then all we need to do now is add our plus c, because it is an indefinite integral. And here we go. This is the answer for this problem. Anyways, I wish y'all all luck on your AP Calculus, either AB or BC exam. Let me know if you need any further review, and follow my TikTok page, or keep an eye on my YouTube. I will try to post more as the semester ends for my school. Anyways, I'll see y'all later, and goodbye.